So, thousands of physicists, engineers, computer scientists, and even modern age seers have worked at it for the last 20 years. It was a spectacularly hard endeavor, but it is finally over. It is happening as we speak. At the CERN laboratories in Geneva, we are trying to, working 24 hours a day to uncover the mystery of mysteries, finding out what is the stuff that the world is made of. Now, you may remember from your high school studies that atomic nuclei are made of tiny things called protons and neutrons. But inside the protons and the neutrons, there are tiny, small, hard things that are named quarks. Now, you might not know what a quark is if you went to study before 1975. So how about going back there for an update? Because, in the last 50 years, physicists have made huge steps forwards in the understanding of matter, the fundamental level. We know it's quarks and leptons. And these things bind together and exchange and interact by exchanging force carriers, things that we call bosons. Now, we have learned how to compute things. It's a pretty scheme. And we've learned how to compute things with these particles, but we are not satisfied because we studied the classics. Indeed, the Greek philosopher Socrates is related to, I put it the best way, 2,400 years ago. En ida oti uden ida. I know I don't really know. We know there's more out there to know than we got to know so far. And further, we even know we have not understood yet a crucial property of matter. What is generating the mass of elementary particles? In other words, why does a proton weigh so much more than an electron? So let's go back to the quarks. We know they are inside the proton, but we actually have never seen them. But we know they're there. It's actually a no-brainer. If I can kick it, it exists. We physicists are very practical people. And we do kick them quarks. We throw a proton against another proton, and from the spectacular mess that is created out of these collisions, we are able to infer that what is inside the proton. It's like you're traveling in the highway, carrying a case of whiskey in the trunk of your car, when you're hit by a truck coming the opposite direction. Okay, not much remains of what was in the car, unfortunately, but from the spectacular debris that comes out, people that come out and pick up the remains might be able to tell whether it was Jack Daniels or Glenfiddich you were carrying around. That's what the Large Hadron Collider experiments do. They throw a proton against another proton at the speed of light, and they examine the remains of these powerful collisions. And from the produced debris, they're able to tell what happened inside. This is what happens when a collision is analyzed by our experiments. So it's actually Einstein that told us that energy can turn to matter. So there is a difference with the car and the whiskey analogy, in that these collisions, these powerful collisions, can actually create new states of matter. So the LHC accelerates these particles to the speed of light, and then this collision turns energy into matter, and new fundamental particles can be created. And so we want to know all about these new particles because they could revolutionize our world. We want to know everything about this. So we built the LHC, a 27-kilometer-long tunnel, 100 meters underground, tightly packed with powerful magnets and cutting-edge electronics surrounding a narrow vacuum pipe. That's where trillions of protons run in opposite directions until they hit each other in the core of these humongous detectors 40 million times a second. So you see, these particle collisions create new states of matter, and we want to know what's happened. Here is a picture of the Large Hadron Collider, and you see the tunnel that holds the magnet where the protons run, and the experiments that are looking at these collisions. Now, I want to show you the very complex CMS detector, one of the two main detectors that we do physics with at CERN. It's built like an onion, layer on layer of precise devices that are capable of tracking the particles that come out of the collision, determining their energy, and figuring out all that happened. It's a marvelous structure, but I have little time to explain to you how it really works. It's actually better if I show you a few event displays, the ways that these giant microscopes can actually interpret the collisions that take place inside these detectors. We actually take pride in making these event displays as cool and colored as possible, and we draw curved lines to represent the trajectory of charged particles as they bend in the magnetic fields, and we draw blocks to represent the energy they leave in other sensitive detectors. It's actually pleasing to the eye to look at these things, but to you it might all look unintelligible and chaotic. But to trained eyes, actually, these event displays allow the instant understanding of what went on when this collision took place. Oh, there's a muon coming out, and that's a jet. That is a quark that exited the collision. So when you analyze many of these events, you are capable of putting together statistical information and figure out whether new particles have been created or new processes have been generated. So, did we see anything new yet at the Large Hadron Collider? Well, I can let you know about this by Peter here.
Hey, thank you. Okay, so unlike Tommaso, I'm a theorist, not an experimentalist, and we have much less sophisticated equipment. This is the most sophisticated piece of equipment that we use. So it's so we're also a lot cheaper. And yeah, but what theorists have been doing for the last 30 or 40 years is kind of waiting for this machine to work. Have been developing more and more exotic theories of the exciting things that might be happening at this new energy scale that is being studied here, and the results that have come out of this machine, even the initial ones that come out during the first year, have really kind of revolutionized our subject and really had a dramatic effect. So so one thing that theorists had theorized about this was that maybe the LHC would create miniature black holes. And this had gotten even into the newspapers. There's some danger that such black holes would expand from Geneva and destroy the entire world and universe. But anyway, well, nothing happened. No black holes. So no black holes at the LHC. And then there was, let's see. Then the next thing that theorists had theorized was that, well, maybe there are extra dimensions, and they're just the right size that in the LHC you'll be able to see evidence for them. So maybe there are extra dimensions. Well, anyway, the LHC says no extra dimensions so far. If they've looked very carefully, nothing at all like that. So that hasn't worked out. Then another very popular idea is the idea of string theory, of strings. And so there's one possibility was that strings were just the right size so that we hadn't seen them until now, but they would show up in these new experiments at the LHC. Anyway, same problem. No strings, no evidence of strings. Then one possibility that has gotten the most attention among theorists and people have devoted the most effort to is something called supersymmetry. And there, the idea of this is that each particle has a so-called superpartner, which is a particle of a much higher mass but similar properties, and it's related by this supersymmetry. Well, kind of pretty much the same problem. No supersymmetry, no evidence of supersymmetry. So where theorists are now is kind of a little bit like this. This is where, a lot of the theoretical landscape is this kind of rubble, and but this was actually kind of expected. If you really look carefully at all of these ideas, despite all the attention they were getting, they really all had kind of serious problems and weren't that convincing. But there was one idea which we which we've been pursuing for even more than 30 or 40 years, which we actually have a lot of evidence for and a lot of reason to believe, and which we really do actually expect the LHC to tell us something about. And this is the idea of the Higgs particle. Let's see what's. Oh, and so now this is actually intentional. So I wanted to tell you kind of what is the Higgs particle about, and why is the subject is kind of hard to understand. Well, to really understand the Higgs particle, what we're thinking very deeply about the vacuum, about nothingness, and so this is what theorists are sitting around thinking about, and it turns out that the vacuum actually it doesn't seem to be doing anything interesting, but it actually has an incredibly complex and sophisticated structure, and really understanding particle physics is about understanding that structure. So what actually we do, what Tommaso and his friends are doing from the point of view of a theorist, is that they're banging on the vacuum. So we don't really care when these protons that they've decided to collide, we're not so interested in the fact that they're protons or studying them, but what they're doing is they're dumping a lot of energy in a very, very small location and exciting the vacuum and telling us something about its structure. Let's see. So now what I want to tell you about is this idea about the Higgs particle, about what it is, and it's a subject that's not really easy to talk about in a few minutes. But I want to tell you about an analogy which has been a huge part of the subject and which has had a lot of influence, which is the analogy with a metal, just a piece of metal, and how this behaves. So if you look at this, what you got the positive signs are a lattice of atoms, and the negative marked things correspond to electrons that can move around in this lattice of atoms. And in a normal conductor, what happens is these electrons move around and scatter against each other and scatter off the atoms. And when you apply a voltage to it, some current goes through of these particles and encounters a certain resistance. Now, it turns out there's some much more interesting particles, some much more interesting states of matter, which are unlike normal metals, are so-called superconductors, where electricity can travel with no resistance. And these were really first understood in the 1950s, and this is kind of a complicated graphic, but the main point is the up in the left-hand corner, that what we believe happens in a superconductor is electrons with a spin up and spin down pair together into something called a Cooper pair, and then you have this kind of spinless entity which has lower energy than the two things separate. So they kind of the state of matter condenses into a new state of matter full of these things, and these things can carry current without any resistance. Now, in 1963, Philip Anderson, who was an expert on superconductors, he wrote a paper and pointed out to particle theorists that there's a close analogy between this metal problem and the problem that they were studying of the vacuum, and that one thing that they were trying to do is to try to somehow make an analogous theory to electromagnetism, but that had massive force carriers, that would correspond to changing the vacuum from the normal one to a superconducting one. And that, and then you also had about 6 different theorists who had more or less ignored his paper 2 years before, kind of independently rediscovered this 2 years later. So there's and one of them was Peter Higgs, and so somehow he went out and he got his name on it. Then a couple of years later, Stephen Weinberg and Abdus Salam finally figured out how to really make this idea work, to get a unified theory of electromagnetic and weak interactions using this idea of a Higgs particle. And they won the Nobel Prize for this in 1979. And so now the theory which they came up with is what we now call the Standard Model. It became part of the Standard Model. And this has been, Tommaso talked a bit about it, but this has been a hugely successful story. This just works incredibly well. And so the story of much of the last 40 years has been theorists trying to come up with some way to do better than this, and failing. But if you look at this graphic, kind of in the back, there's this Higgs boson, and there's this. And if you go back to a picture of Peter Higgs, in the back behind him, there's these equations, and these are the equations for the so-called Higgs field. And this Higgs field is really the simplest possible way of making the vacuum into a superconductor. And this is what Higgs had worked on, and this is what is part of the Standard Model, and this is what we really would like to be able to test. And one way of testing this idea is that this field should have, it's a quantum field, it should have quanta, which means that there should be some new particle we've never seen before corresponding to this field, and that's been called the Higgs particle. And the theory tells us exactly what the properties of the Higgs particle are supposed to be, except it doesn't tell us what its mass is. And so what this is all about, and the big question which is before us and has been bothering us for 40 years is, does this Higgs particle exist? And if so, what is its mass? And the really exciting moment, this exciting moment in history, that the Large Hadron Collider is finally getting to the point of collecting enough data that we should just be able to start to see signs of this emerging very soon. And what I'm hoping to get Tommaso drunk this evening and get him to tell me is what's really going on and whether they found it or not, and if so, what its mass is. We'll see. Anyway, so two things can happen later this fall or in the next few months. One is the Higgs particle will be found, and then it'll be Nobel Prizes for everybody. So you get one of our problems is going to be who to give the theory Nobel Prize to. So you got 7 of these people, and one of them unfortunately died recently, but you can only give it to 3. So we're going to have to wait for three more to go. The other thing is who to give the experimental Nobel Prize to. So we can give it to Tommaso, and that would be a good idea. But the problem with that is that he has a lot of collaborators, like 3,000 of them, and they might actually have something to say about this. So we'll see. Anyway, I guess now I'll turn it over back to Tommaso and see what he's willing to tell us. Oh, sorry. I blew it. One more thing. The really exciting thing, the exciting thing I forgot to tell you. Sorry. The exciting thing is if the Higgs particle doesn't exist. This is what we really want. If the Higgs particle exists, you're going to hear all that. It's a wonderful story. Everything is great, and theorists are wonderful, experimentalists are wonderful. But it's going to be very kind of depressing for us because we've learned nothing really new except the mass of this particle. If he finds out the Higgs particle doesn't exist, it's actually going to be a lot more exciting. It means that we actually don't understand anything. Everything we thought we knew was true for 40 years is really wrong, and we have this incredibly impressive piece of apparatus which if we figure out how to use it just right, will tell us what's really going on if it's not the Higgs particle. So that's what we're waiting for, and let's see what Tommaso has to tell us.
Yeah, thank you, Peter. Indeed, my experiment has been sitting on over twice more data now than was published at summer conferences, so a little bit more than a month ago, as graph behind my back screen. It's integrated luminosity, so we call it. So right now, there's 3,000 of my collaborators in the CMS collaboration, and as many in the Atlas collaboration, that are working feverishly to produce plots like this, and these 3,000 people are looking at all the possible ways that the Higgs particle can be detected, because there are a number of them. And they are maybe seeing the first glimpse of this particle in these collisions. So maybe we have a result there. So am I allowed to tell you whether we have finally found this particle which has escaped detection for the last 40 years? I hesitate because, you all look trustworthy, and I'm willing to buy that you will keep this information within these walls. But Peter is such a loud mouth with his blog. It can't be relied upon. See, the problem is that when in my blog I say something secret about my experiment, and I let go with some new information, I get 3,000 people all angry at me. And, okay, I can live with the standard punishment, like a ban from presenting results of physics conferences. That happened once, actually. But, in 3,000 people, there's always an athead or two who are willing to do very bad things to you, like scratching your car. Now, that would be annoying, of course. Well, Peter here, he has no problem because he only gets the good press when he lets go with an anonymous comment saying that a new particle has been created, because he only gets the good press. Experimentalists can do nothing at him because he doesn't fancy going to physics conferences, plus he doesn't own a car. So, am I allowed to tell you whether the Higgs boson has been finally found and tell you all about it before I get treated with some very good wine tonight? I don't think so. No, but I can certainly tell you something. I can tell you what the Higgs boson mass is if it exists. The Higgs boson mass is an all-important parameter because it determines both how this particle is created in the collisions, whether you have enough energy to create it, and also what signatures it gives rise to when it decays. So in the past, this is the Higgs particle bouncing around, and this is the values of the Higgs boson mass, and we don't know anything about it. But then the Lab 2 experiments at CERN have managed to actually determine that the Higgs boson mass must be higher than 114 giga-electron volts, if it exists. That's something. Giga-electron volts, don't worry about what it is. It's more or less equivalent to a proton mass, a little more than that. So below 114, whatchamacallits, no Higgs boson. And then this other thing happened that recently the LHC experiments had ruled out that particle cannot even be heavier than 145 giga-electron volts. So we know that the Higgs boson, if it exists, has a mass within this narrow window. So I can tell you that the Higgs boson mass is 119 giga-electron volts, give or take a few giga-electron volts. You can tell your grandma if you want, but please don't tell Peter, okay? Oh, okay. So I think this is it. Oh, okay. So you're not allowed to do that, you know, Peter. That's not the way it works. You know, this is actually a fake, but if you want to know news about these particles, faster than the speed of neutrinos, you might come to our blogs first for news about it.
Thank you.
Thank you very much.
Thank you very much.